Hello and welcome to this video where we are going to learn how to create a basic convolutional neural network to perform image classification. We are going to use a TensorFlow framework, Python programming language, and Google Colab as our editor. We did a previous video on how you can be able to load data into Google Colab and pre-process the data using TensorFlow. And if you have not watched that video, I have left the link to the video in the description below. You can click on it and watch the video. I highly encourage that you watch the video because it will help you understand where we are coming from in this particular video and how we were able to load our data in Google Colab and even what we have done in as far as pre-processing the data is concerned as a way of preparing our data set for purposes of feeding our neural network. Now, I'll just highlight quickly on what we did in that particular video, and then where we have continued in this particular video where we have made changes. I'll be more deeper or I'll be more thorough in terms of description. If you are writing live codes, you can pause the video and write codes. I highly encourage that you do live codes because I have tested this code and it is working perfectly. So the very first step that we did was to import TensorFlow. So you can import TensorFlow as PDF and you can be able to do that very quickly. If you're not using Google Colab, you're using other Python editors, it is important that you check the version of your TensorFlow so that you can ascertain that at least you have version 2 point something. In this case, I'm using version 2.12. This is the code to check the version of your TensorFlow. Then now, in the previous video, we did show you how you can be able to link your Google Colab to your Google Drive using this particular code that we have over here. After that, we showed you how you can be able to fetch the data that is available in your Google Colab and display it here, rather the data that is available in your Google Drive and display it here in your Google Colab, as well as split the data into a training set and a validation set. More details on the specific of what these values are represent, you can be able to find them in that video, and the description is below. And in this case, we can see that we had a total of 3,670 images which belong to 5 classes. And after doing our validation and training split, we found out that we are going to use 2,936 images for training and 734 images for validation. As to whether that is an ideal split or not is a discussion that one can have. Then we were able to define our batch size as well as print the image labels, and you can see the various labels that we have over here: daisy, dandelion, roses, sunflowers, and tulips, representing each of the classes. And I said that it is important that you note that our model or our uh, program here will be treating these image labels as arrays, and therefore they are going to be labeled starting from number 0 all the way to size -1, which is array 4. Then we went further and we introduced this concept. This one is new for this particular video. And what we have done here, rather than just having a validation set, we decided to introduce something known as a testing set so that you can be able to evaluate how well our model has performed. And in this case, we have taken the data set that's available in the validation set and split it further into a testing set. You can see where you have been able to split it. This is the code for splitting the data set because we really want to, at the end of the day, be able to evaluate what the model is able to do. After that, we went further and did standardization. In our previous video, we had done standardization for just the training set and the validation set. But in this case, since we have created another set here, which is known as the testing set, we as well did standardization for it. And this is the code for that particular standardization in this last line over here. It works just the same way as we standardize the training and the validation set. So it is important that you make sure that you have as well standardized yours and make sure that you have introduced the training set in your case so that you can be able to follow up this tutorial correctly. But if you don't desire to evaluate your model with a testing set at the end, then you can ignore the testing set and just work with the validation set. After that, in our previous video, we displayed this particular images. That is, we took the original images, we displayed them together with their labels, and you can be able to see that the specifics of what these codes represent. We did them in the previous video, which I encourage you to watch so that you can be able to understand it more clearly. Then we went further and used TensorFlow to do some basic preprocessing, which include random flip, random rotation, and so many others. And all these variables, we discussed them thoroughly in that particular video. Then we displayed the images that we had done pre-processing on, and we were able to get this particular image, which is image that belongs to array 3 or belongs to index 3 in our array. And it's a sunflower image, and we explained how the various preprocessing have taken effect in this particular image, and how you can be able to differentiate this one from the original images. And that is something that will help you understand how neural network will be able to view our image once we feed it with this particular image. So during our previous video, we left it at that point where we did array preprocessing, and now we are continuing from there. So our video today begins at this particular moment. And in this case, what we have done now is that we want to create a convolutional neural network that we're going to use to classify this data set that we have over here into the respective 5 classes. So we are going to train the first create the architecture of the neural network. We are going to train it and we are going to evaluate it, which tells you that this is a very comprehensive video. So the very first thing that we do is we first create a variable known as number of classes or num_classes. And for us to be able to assign it values, we use a function known as len, which basically defines the length, and then we pass a variable known as class_name. If you go back to where we were doing our pre-processing over here, we defined a variable known as class_names, and you can be able to see it here. And these are the various names. So what is the length of these names? We only have 5 names. So in this case, num_classes will have a value which is 5. So I believe that you have been able to get that very, very clearly. After that, the next thing that you need to do is to install something which is known as TensorFlow add-ons. If you're using add-ons for the first time, it's important that you use pip install TensorFlow add-ons, especially for those who are not using Colab. And then once you do that, you import TensorFlow add-ons as TFA. The reason as to why we are doing this is because there are some evaluation metrics that require us to use this TFA add-ons. And you find that some older versions of TensorFlow really require you to import this, while as newer versions may not necessarily require you to import that. But to be on the safe side, always import it so that you can be sure that you have the requisite library. So in my case, you can see that this requirement is already satisfied because I had already imported it previously. Now the next thing is a very important step, which is known as creating a one-hot encoding. What is a one-hot encoding? When you have data like this, and you can be able to see it very clearly, you can see that here we have categorical data. In this categorical data, each image belongs to a certain category in that particular subfolder where it is saved. Like now, you'll have an image which belongs to sunflowers, you'll have an image which belongs to roses, you'll have an image which belongs to the dandelion. But now, very few algorithms are able to do this, to understand these categorical labels. I believe it's only decision tree that can be able to understand those categorical labels, but now decision tree is also limited because it cannot be able to achieve the kind of performance that a neural network would. Equally, it would require you to have external feature extractors, which give you a very huge task to do. And considering that it is also a classical machine learning algorithm, it is very limited. Now, for us to be able to convert these categorical data into numerical data, then we need to use a one-hot encoding. Basically, what a one-hot encoding will do is that it will assign index values to the arrays, to the labels that we have in this particular array of our data. So say an example, come here and take these image labels that we have over here. We have diced, dandelion, roses, sunflower, and tulips. So what one hot encoding will do, it will loop through each of those images contained in this folder known as diced and assign it index 0, dandelion assign it index 1, roses assign it index 2, sunflowers assign it index 3, and tulip assign it index 4. So now, anytime you are running your model, it will be displaying them in form of indexes, and this will make it easier for your model to work. After creating that particular one-hot encoding, something else very critical here is that we need to optimize our training process so that our model doesn't take too much time to load our data set, neither does it take too much time actually convert our data into the required formats. So to do that, we need to go another one more step, still under one hot encoding, which is basically do what we call data out tuning as well as data prefetching. So we take the training set and we map it with this input preprocess that we have created here. This is a function in Python. And anytime you see the word def and then input preprocess, there's a function. And in this function, we defined an image and a label. And if you go back to our code, you will see where these variables are coming from. For instance, if you come here, you can see here we have a variable which is known as image. And if you go to where we scaled our data, you can see here we have both the image and the label. So it is taking the image and then a requisite label. And after doing that, what it is doing is that now it is creating a one hot. So converting the categorical label, which is basically the label containing the one, let's say sunflower, to a one hot, which is now an array index. And it is using the method known as tf.one underscore hot. And then you pass the label. Let's say in this case, the label is sunflower, and then number of class. If the classes are 5, then it will take that label and check it. Where does it appear among those 5 classes? And then it will assign it its requisite array index. After that, it will return for us an image and a label. Remember, functions do have a return type. In this case, it will give you an image of, say, a sunflower and a label that corresponds to its specific array index. So after you do that, now you come here and take your DS training data set, and then you map the data set to one, the input preprocess, which is this function that you have created here. So you have taken it, and now you have mapped the images there to their respective labels, and then you do some further parallel calls. And in this parallel calls, what you are doing is that you first want to prefetch the data such that if you're using batch sizes of 64, like we are going to use in this case, and the first 64 images are currently being worked on in the model. So what this one will do is that it will prefetch the next 64 images so that they are somewhere in the pipeline, just like how caches work in our computers, so that your model doesn't have to take so long. Neither does it have to take a lot of time to fetch this data. And then after it does this prefetching, it will do all the formatting that you have done to your data when you are doing your processing very quickly for you to be able to do that. And that's why you can see over here in each of these data sets, we have defined a prefetch method, and then inside that particular method, we have called output so that it can prefetch our data and format it very quickly to the desired format, save on our time. So after you create this one hot encoding, what you eventually get is a data set that is ready for our neural network to understand. And now, once you have that data set, the next step that you need to do now is go ahead and create a neural network. And since we are using TensorFlow here, we are going to create what we call a sequential neural network. A sequential neural network simply means that it moves from the input layer all the way through the hidden layers. And in those hidden layers, there could be some convolutional layers inside them. There could be some max pooling layers inside them. And there could be some fully connected layers inside them, or up to the where we have the output layer. It follows a sequence. Now, for you to be able to do that, you are going to use a method which is known as tf.keras.models.sequential. There are some materials which desire to use tf.keras.sequential. They avoid the models here. But whichever format that you use basically depends on the version of TensorFlow that you are using, as well as your desire as the developer on how well you want to be precise in terms of what you are creating. I prefer to use tf.keras.models.sequential so that I'm more specific that I'm working with the TF models. If you're just creating a basic neural network without CNN, there are some layers here that do not require, but in this case, we are creating a convolutional neural network, we must input some layers here, we must include some layers here that are very, very critical. And for purposes of image processing, it is advisable that you use a convolutional neural network and you avoid using just the ordinary artificial neural network, because what we say is that a convolutional neural network, the convolutional layers play a very critical role of extracting the features from the image, and thus they save you the effort of having an external feature extractor that would otherwise require to extract the features. Therefore, it means that if you are to use the ordinary neural network that doesn't have convolutional layers, then you would be required to use external feature extractors such as Hog feature extractor and so on, which would be a tedious task. And many of the image processing models that we have seen in the industry, including the most powerful ones such as VGG nets efficient nets, residual neural networks, and so on. All of them use convolutional neural networks because those convolutional layers play a very critical role that make your model be more robust in terms of feature extraction. So let's go ahead and create this network. So we first define a variable known as model. This variable known as model is the one that is going to is a variable name that is going to house our model. So anytime we refer to model, we'll be referring to whatever is found within this particular sequential model that we are creating over here. Then we call our method tf.keras.model.sequential. We open a curly brace and we open this square bracket. Anytime you see a square bracket somewhere in programming, it means that whatever is in there is like an array, and therefore once you call the variable name, you are calling the elements that are contained in it in totality. Then we create our first layer. The first layer is usually known as the input layer. It's a very critical layer, and there is no neural network that can work without the input layer. And when you are creating the input layer, something very useful for you to remember is that you don't really have to define the number of neurons that the input layer will have, because basically the number of classes that your dataset have will automatically define the number of neurons that your input layer will have. But more important, there are elements that you need to define on your input layer, which include the input shape that you want to have or you want your model to have. So let's go step by step and understand what we have here. So we use a method. So the very first thing that you do is that you call tf.keras.layers.conv2d. Conv2d stands for convolution, which means that it's a convolutional layer. And in this case, you are talking about a two-dimensional convolutional layer. We have three-dimensional convolutional layer, we have two-dimensional convolutional layer, and we even have a one-dimensional convolutional layer. So whichever you want to use basically depends on the type of features that you want to extract. The 2D is the most common ones because it is able to extract even high-level features from the images. And we have an entire documentation in TensorFlow about what a 2D layer contains. And there are so many hyperparameters that are contained in it that you can be able to pass. If you look at this documentation that we have over here, you can see that a 2D layer has several hyperparameters that we have, and you can be able to argue with all these hyperparameters. The first one is known as filters. And when you talk about filters, like in our case, you can see we have used that a variable name, or we have used a size which is 32, which is that it will be able to use filters of size 32 to extract data from our images. Then, since it's a 2 by 2 convolutional neural network, we need to pass two values here in the kernel size. And when you talk about the kernel size, the mathematical function that basically tells us how will it be able to map the original image and the features that it is extracting. So if it was a 3D, we would be required to maybe pass more values here. But now, since we are just using a 2D, we just need to pass two values in this case. Then we need to pass an activation function. In this case, you're going to use what we call the rectified linear unit activation function. It's a very popular activation function. And the role of an activation function in a neural network is basically to, just like the name suggests, to activate a neuron. In this case, what happens is that it takes the input that the neuron receives, it has a weight and a bias, and then computes the weight and the bias and sees whether or not it meets the required threshold. If the threshold is met, then the neuron is activated, and thus it can be able to pass the data to the subsequent, or to what we call the succeeding neurons. If it is not, it has not met the threshold, the neuron is killed, it is not activated. There are quite a number of activation functions that one can be able to use. We have what we call the sigmoid activation function. We have the tangent activation function. We have the leaky rectified linear unit activation function, and so on. I've decided to use the convention, what is many people use, which is the rectified linear unit. And you can read the documentation on the differences between all those activation functions and the strong points and the weak points of each one of them. Then you can come here and define our input shape. In this case, when you talk about the input shape, these are the dimensions of our images. In this case, we want them to be 512 by 512 by 3. What do we mean by these figures exactly? These are the length and the width of our images, and 3 shows that it is an RGB image, or what we call a colored image. If it was a black and white, or what many would call a grayscale image, then the value here would be 1. So whenever you put 3 there, the neural network knows that it is a colored image. And like I said, you can be able to see that there are quite a number of hyperparameters you can play around with here. So many of them, including kernel regularizer, bias regularizer, activity regularizer, kernel constraint, and so on. So if you're doing this for purposes of research, it's good that you understand all these regulators that we have over here and how you can play around with them to optimize your neural network. But if you just want to learn how to create a basic one, you don't really need them. You can just work with the defaults. Then after having a convolutional layer, the next very important layer that you need to have is a max pooling layer. So a max pooling layer plays a very critical role because it is used to do downsampling of your output. And in this case, when you consider the output, or when you consider the input of the max pooling layer, rather, it is the output of the previous layer, which in this case was a convolutional layer. So what the max pooling layer here will do is that it will take the length and width dimension and then have a kernel size of 2 by 2. And with this kernel size of 2 by 2, it will take the largest pixel values from that particular window that kernel size will map, and then it will output it as, or will compute the max value of that particular window, and then give it as the output. This helps in eliminating some unnecessary feature maps, because if you take scenario in which an image is considered to be having pixels, and it is these pixels that are considered to be relevant for purposes of displaying or differentiating one image from another, then not all pixels really play that role, because some pixels could be irrelevant, and therefore max pooling helps in eliminating those irrelevant pixels. So the next thing that you need to do now is come here and create a dropout layer. And a dropout layer, what it will do is that it will kill some neurons in your neural network with the sole purpose of eliminating neurons that may end up overrunning the data so much and making the model to be less generalizable to new data sets. And in some cases, depending on how you use it, it can be used for purposes of avoiding overfitting. Whether or not you have dropout layers in your neural network basically depends with the nature of your neural network, as well as the kind of task that you want to do with your neural network and how your data looks like, and whether where you place it exactly in your neural network could differ from one to another. There is no standard way of where you should place a dropout layer. You can have as many as possible, and the value that is found inside the dropout layer defines the percentage of neurons that will be killed. In this case, I have 0.2, which means 20% of my neurons will be killed by this dropout layer. After that, you go and create another convolutional layer. In this case, I have also created a convolutional 2D layer, but now here I have defined a filter size of 64. In the first one, I had a filter size of 32. Remember, all these are hyperparameters. You can put the ones that you desire. Then I have defined also a kernel size here, which is 3 by 3, and I have an activation function which I have equally used Peru. But notice the difference between this one and the first one. In the first one, I had an input shape because it was the input layer. However, in this one, I don't require an input shape because this is a middle layer. And then I have a max pooling again, a dropout again. And then that one is followed by a flattening layer. And then after the flattening layer, I go to what we call the fully connected block, or the fully connected layers. And in this case, I have I create a fully connected layer in TensorFlow. We use the dense method. So you go tf.keras.layers.dense, and then you define the number of neurons. In this case, I've defined it to have 128 neurons. And you can define any number of neurons here. There's a hyperparameter. Then define an activation function, which is Reru in this case. I like using the industry standard, which is Reru. And I've put another dropout here, which is 0.2. This dropout can easily improve or downgrade your performance. So it's upon you to check. You will need to do a lot of looping for you to easily tell which is the ideal dropout for you, and even how many you should have in your case. So having done that, we have seen the input layer here. We have seen the hidden layers, which are read from where you have this max pooling 2D up to where we have this dropout, and we have seen that this is called a fully connected layer. Now, the last layer here that we have is the output layer, and this output layer should be a fully connected layer. Now, the output layer, the only difference between it and this fully connected block that we have over here is that you need to define the number of neurons that commensurate to the number of classes that your model is expected to classify the images into. In this case, my model is expected to classify the images in the 5 classes of the flowers that I have, and that is why I have 5 neurons there. Each neuron represents a class. Then you need to have an activation function. For purposes of classification, we have 2 main activation functions that are used. We have the softmax activation function, especially if you are dealing with multi-class labels, that is, you have more than 2 labels. And we have the sigmoid activation function, which is basically used for what we call binary classification. So if you see somebody using the sigmoid there, it means that their model is doing binary classification and they should not lie to you that they are doing multi-class classification. For softmax, that one is used to do multi-class classification. Now, after you have done that, you already have your model now. It is well created, but it's just a shell. It cannot do anything. So you need to go some further steps, and now you need to compile it. You need to also give it some more values, such as what is it going to use to learn, which optimizer is it going to use to learn, how is it going to compute the loss, which are the metrics that it is going to consider when it will start training, and how will it evaluate your data. So to do that, you go to the first thing here. You call a method known as the compile method. When you are calling a compile method, it's basically like you are building the model now, and you want to pass more values to that particular model in readiness for it to fit the data set that you want to train. And in this case, the values that we pass here differ from one model to another, but here I have just highlighted the basic values. And the first one is known as the optimizer. Optimizer is used to optimize the learning or the training that the model will undergo. Many of the optimizers that we have emanated from the stochastic gradient descent, and therefore they are usually known as the gradient descent learners. We have quite a number that exist. We have the base one, which is known as the stochastic gradient descent. We have more adoptive ones such as the Adam. We have even a higher version of Adam, which is known as Adamax. We have Ada Delta, we have Adagrad, and so on. You can read the Keras documentation of the difference between all these optimizers. In this case, I've selected Adam. And just to mention that apart from just selecting Adam, Adam itself has also some hyperparameters that you can consider, which include something such as the learning rate. It also has things such as even the speed at which you wanted to learn, and you can even define several other hyperparameters. So I would highly recommend that you take the Keras documentation on each of these optimizers and see the various hyperparameters that they have. Then after that, I define a loss function. In this case, my loss function is going to be categorical cross entropy, something else here to define. We have several loss functions that exist, but the most commonly used one are the categorical cross entropy and the binary categorical cross entropy. So what is the difference between these two of them? The categorical cross entropy is used for multi-class classification, while the binary one is used for binary classification. And therefore, it's very important that you use the right one, otherwise your model will not work correct. Now, the loss function is used to easily tell how your model is learning and how it is able to reduce the loss. The loss is basically the difference between the actual value and the predicted value. So when you see that your loss is reducing, it means that your model is performing well. And if you find that your model is not reducing the loss that it is making all through the training iterations that it is making, then the model is not performing very well, and there is need for you to review whether you need to optimize it further. Then after that, we need to now evaluate our models. So we define the metrics that we're going to use to evaluate our models. And in this case, we are going to use quite a number. We are going to use accuracy as one of the metrics. Then we are going to use recall. So accuracy, you can just define it directly under this method here. Recall, you need to call tf.keras.metrics.recall. Then you pass the name as recall. You do the same for precision, and then you do the same for F1 score. And when you're defining F1 score, please be precise on the number of classes that you want to consider. Then you can print the summary of your model. Now this is like a display of what your model now looks like, and you can be able to see it all the way from the input layer up to the last layer, which is the classification layer. And now you can even be able to draw this summary for visualization if you want to understand it better. And it will give you the parameters that it has. It has a total of 176,357 parameters, and you can be able to tell where these parameters are coming from. For example, you can see that the dropout layers do not generate any parameters, and you can as well see all where we have dropout there are no parameters. Max pooling layers equally do not generate any parameters, and parameters are generally generated by the convolutional layers and the dense layers. And from the look of things, you can easily tell that the fully connected layers have the highest number of parameters, like you can see over here. If, for instance, we change this number of neurons from 128 to something like 50 or even 52, you could find that these parameters would reduce. The key thing here to note is that when you have very many parameters, you could have a very bulk model, While equally, when you have few parameters, you could have a very weak model. So the exact balance in the terms of number of parameters is work of research that you work on as a developer to find the best fit. That's why we call it creating an ideal architecture, because you cannot just pick an architecture from somewhere and then it fits there. So creating an ideal architecture is something very, very critical and something that you should consider doing. Now, having looked at our model, created it all the way from here, compiled it, we have printed our summary. The next big thing now to do is to come here and now think of how we are going to train it. For us to be able to train it, I want us to consider something known as model callbacks. Callbacks, what they usually do is that they save the progress of our model, and they help us anytime that we want perhaps to use that particular model for a certain task, or we want to improve on it. We can easily just pick it and then we improve on it. However, note that when you're doing these callbacks, you need to be very careful on what exactly you are evaluating or what you're considering, because there are several parameters that you need to pass here. You also need to pass where to save your model. Let me just go ahead and pass several things here. There's something known as early stopping. Early stopping simply means that if you do quite a number of epochs and you realize that your model is not improving in performance, and in this case you define the metric that you're considering. In my case, I have considered the validation accuracy, and the patients have considered to be 10 epochs. If my model goes for 10 epochs and the validation accuracy does not improve, then it should stop, because further training will only result to overfitting. Then I come here and define my model checkpoints. I call the method known as model checkpoints. I define the path where I want to save it. I showed you how to create paths, and you can be able to do that in your Google Drive. Once you define the path where you want to save it in your Google Drive, you just need to go to your Google Drive and create a folder known as weights. And since you connected your Google Drive there, all now that you need to define is the name of your model here, my CNN underscore model v1.h5. H5 is one way of saving models. We have several other methods, but the industry standard is H5. And then you're monitoring the validation accuracy. So what will happen is it will be monitoring the validation accuracy, then it will only save the best. So in the first validation accuracy, let's take an example, it is 10. Then in the subsequent epoch, it improves to 12. So in the first one, because the first one it will save 10, the second one it will save 12. Let's say in the fourth one, it reduces from 12 to 9, it will stick at 12, so it will have saved 12. So it saves the best. Then it does not save the architecture per se, it only saves the weight. It only saves the weight. So it will not have saved much of the architecture and the data set and so on. It will only save the weights. And in subsequent videos, we'll show you how you can be able now to take the model that you saved and modify it, or even take the model that you saved, train it further and see how it can be able to perform. Then after that, the next thing now is to go ahead and train it. When you are training a neural network, there's something that we need to define here known as epochs. Epochs basically refers to how many iterations do you want to train, how many times, if I may use simple English. But in programming, you can simply call it iterations. How many iterations do you want it to train? In this case, since I didn't want to take a lot of time, because the number of epochs can really range. There are some who even train for 200 epochs, 250, and the number of epochs that we use basically defined by the kind of neural network that you are creating. And since this one is just for a YouTube video, generally I'd consider 3 epochs to be sufficient for me. But in your case, you can have as many as you desire, and there is no standard number of epochs. It's basically your responsibility now to define which one is best for your case. And that's why early stopping is important, because if you put on 100 epochs and then at maybe at epoch 70, all the way from epoch 70 to 80, nothing has improved, then the model needs to stop training. All right, hope you have noted that. So we define a variable known as hist. Hist is the history. We want to have this history for purposes of plotting. So then we call a method known as model.fit. If you have been watching my videos, you know that model.fit is a method that is used to train any machine learning model. So then we pass the variables here that we want to pass. We want to train it with a training data set. So ds underscore train. We want the number of epochs to be these 3 epochs that we have used here. And we want to validate it. As it seems, we actually want to validate it using the validation data set. We pass dsc underscore validation. Then we come here and this model checkpoints that we created here, and we create a variable known as callbacks is equal to the model checkpoints that we created here, and as well as early stopping, which means that we wanted to stop if it is not improving. Then our batch size is 64. Remember, since we had created a variable known as batch size up there, you can just put batch size comma, but if you want to be more specific, you can put 64. Verbose is equal to 1. Verbose is basically how it will be displayed as a training. Do you want it to show you this progress here? Do you want it to show you it is in which in each epoch has some gradient steps that it takes. Like for example, this epoch, each epoch is taking 92 gradient steps. So do you want it to show you those steps it is taking? Then once you run that particular cell, it will start training. It will go to epoch 1 over there, which is the first training iteration, and then it will take 92 steps in each case. And in this case, you can be able to evaluate quite a number of things here. You can see that the loss was at 1050 accuracy. You can see it at the first training accuracy. The first one here shows the training accuracy, which was 30.01. You can see the recall, you can see the precision, and you can see the F1 score. Now, if you take this particular, this particular validation accuracy that we have over here, or sorry, the training accuracy that we have over here, we also need to know what is the validation accuracy. So what do we see here? We can be able to see here that in epoch 1, our model was able to register a validation accuracy of 24.932, and it has saved it in my drive. It's telling me that it has saved it, and you can actually go and see other validation results further here. Like for example, if you navigate here, you can see the validation accuracy, the validation recall, the validation precision, the validation F1 score, and so on. And then in epoch 2, the training accuracy improved as well as the validation accuracy. Now it hit 25.2. In epoch 3, the validation accuracy improved to 26.567. So if it was improving in all those three training epochs, it simply means that if we could have trained it further, perhaps it would have improved. But there's something that I want you to note here. There's a very huge gap between this training accuracy and the validation accuracy that we are receiving. And that should ring a bell to you as a neural network developer or as a deep learning expert, that your model is not very efficient, and therefore you need to do something in as far as tuning the model is concerned. And you can come here and display or visualize your training, or visualize your training epoch and see how the training curve as well as the validation curve has been able to perform. Let us just take one metric, which is accuracy, and we use matplotlib for purposes of plotting and displaying, and we use the plot method to define all the variables that we need. These variables we have discussed them so many times, and in this case we have put a hist here, a variable known as hist here, which is this hist that we created here, or the history. So we want to print this history, or we want to display this history, and we want to, in this history, we don't want to display everything. We just want to take the training and validation accuracy and display them. So if you look at this curve, it speaks volumes. That for the three epochs, the training accuracy, which is represented using the blue curve, was improving very randomly. It actually started at 0. Somewhere between 0.30, and it shooted all the way up to past 0.50. Whereas the validation accuracy, yes, it was improving, but at a very slow rate. At a very slow rate. So that communicates one thing, that your model as it is not well optimized for purposes of it performing this particular task. So what do you need to do? You need to come back to your neural network where you created it here. If you look at this neural network, it's a very shallow one. It has very few layers. And in each of these layers, we have just taken the default figures. For example, in this conv2d, I said there are so many parameters that you can consider, like regularizers. You can see them over here. We have not included all these parameters. We've just taken the default values, which are none, 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 and so on. And now this is where your expatriate as a neural network developer comes in. The rest can be history. You can take code from anywhere and copy it, but your expatriate as a neural network developer, this is where it comes in. After you train and find that the architecture that you have is not okay, now defining the ideal architecture for that particular task is the most important task. So now you need to come and reconfigure this architecture, decide, do I have the sufficient number of layers? Really, does it mean that the convolutional layers that I have, are they enough? Are they too much? Do I need to add more dense layers? Do I need to reduce the number of dropout layers that I have? Do I need to increase them? Perhaps do I need perhaps to change the number of filters that I'm using in my convolutional layers, maybe from 32 to 16 or to 128? Do I need to change the values in the kernel size? So all these are now what measures the expert rate of a deep learning developer. And now it's your responsibility now to come in and define exactly what you want to do. Now, since this was just a YouTube video, we are just going to use those basic values, and this was meant to just train you how to create a basic one. We are going to do a subsequent video on how you can now be able to optimize this one to achieve better performance and achieve an accuracy close to 90% somewhere there. And I believe this is something that you are going to benefit from. So having done that, the next thing that you're going to do is now to evaluate our model. Now, when you're evaluating our model, we are going to use the test data set. So we create a variable known as test, and we pass the DS test. And if you go to where we were creating our one hot encoding, you can see our DS test, which is the test data set. Then once we come here, we import something known as metrics. So from TensorFlow add-ons.metrics, you can be able to import other metrics that exist. That is if you want to use them. Then we come here and define the values that you want to evaluate. You can be able to evaluate the raws, accuracy, precision, recall, F1 score, but you may not necessarily need to evaluate all of them. Like in this case, I was just interested in printing just a few. I was interested in printing accuracy, precision, recall, and F1 score. So then you call a method known as model.evaluate, and then you pass the data set that you are using, the testing data set. In this case, I've defined it as a variable known as test. So I have passed the accuracy, precision, recall, F1 score is equal to model.evaluate test to evaluate this data set, then print out the values for me. And you can be able to see here we have our test accuracy, and there's a difference between a validation accuracy and a test accuracy. It's very important that you understand those two differences. That the test data set is completely unseen, and also in this case, when you're talking about the test data set, it helps you to understand the robustness of your model. The validation data set helps you to understand whether or not your model is overfitting or not. It also helps you to understand the best parameters for your model. So validation accuracy is very critical. Validation metrics are very critical, especially if you have not yet achieved the optimal model. It's the one that will help you to know the optimal model. Then after you achieve the optimal model, you subject it to the test dataset. And I highly encourage that all developers use a test dataset because it plays a very critical role. And you can be able to see how it has performed in this particular case. And I will now encourage that you go ahead and improve on this particular model and achieve a better performance than we have over here. So thank you so much for watching this video. Please consider subscribing to our channel, like our videos, put your comments in the comment section below, as well as share our videos with your friends so that they can also benefit. And if you'd like to reach out to us, we have put our email in the channel description. You can reach out to us and we'll be able to custom create a video for you, as well as for any other things that you'd like us to evaluate, more specifically in the area of technology, we'll be able to do exactly that for you. Thank you so much.